In this lecture, we'll be talking about qualitatively evaluating acid strength. Qualitative evaluation is different than what we talked about last time, which is using pKa, which is a quantitative evaluation of acid strength. In this class, we're going to rely almost exclusively on qualitative measures, so looking at two acids and just qualitatively determining whether one is stronger or weaker. We're going to talk about several different factors that we can use to figure out whether a certain acid will be stronger or weaker than another one, and then we'll talk briefly about Lewis acids. Okay, so if we simplify the concept of an acid like we talked about last time, an acid, generic acid, is going to be a proton donor. So let's ignore the base. Let's ignore what it's donating its proton to. On this side of the equilibrium, we have an acid. On this side of the equilibrium, we have its conjugate base. Think about the equilibrium as a scale, right? If we stabilize the conjugate base, products will be favored if A minus is stable. If A minus is unstable, then that means that the reactants will be favored. So reactants favored if A minus is unstable. So what we're going to do for everything from this point forward, we're going to look at stability of the conjugate base. So every time you look at an acid-base reaction, you want to look at A minus, you want to look at the conjugate base and decide what factors are stabilizing it, and that's going to help you determine the strength of the corresponding acid, which is HA in this case. If A minus is very stable, there's going to be a large concentration of A minus, which makes sense, it's stable. If A minus is very unstable, there's not going to be very much A minus. It's unhappy, it's unstable, it's going to exist primarily as HA. So we're going to use that to understand everything moving forward. Okay, so let's look at some examples. Hydrochloric acid is a strong acid. Why is that? Well, the reason is because its conjugate base, Cl minus, is stable. We'll talk about why in the next slide. Whereas butane, or CH bonds, typically are extremely weak acids. Butane is actually one of the weakest acids. The reason is because its conjugate base is extremely unstable. So why is that? What determines the stability of the conjugate base? Well, we're going to look at 5 different factors to determine stability, and I'm going to go over these factors in the order of their importance. So you want to evaluate factor 1 first before moving on to another one. We're going to abbreviate these factors A, R, I, O, S, Arios. The first one that we'll talk about, factor 1, is the atom. So you want to look at the atom that's charged. Remember, what I just said is that when you're determining the strength of an acid, you want to look at its conjugate base. So let's do that. If butane donates a hydrogen, we get a negatively charged carbon. If propanol donates a hydrogen, we get a negatively charged oxygen, right? So we have a carbon with a negative charge here, and we have an oxygen with a negative charge here. We have 2 different charged atoms. And so that's going to help us determine the stability. What we want to look at is the electronegativity. That's going to help us determine which one is more stable. So remember, fluorine is the most electronegative atom, and that electronegativity increases as we go across a row in the periodic table, right? So what you want to remember is that the more electronegative atom is happier with a negative charge. That makes sense, right? Electronegativity is a measure of how badly that atom wants those electrons. So the more electronegative it is, the more stable that it's going to be with a negative charge, right? So if we have this conjugate base here, we have a negative charge on oxygen versus a negative charge on carbon, right? This guy's going to be more stable, right? Because we have the negative charge on the more electronegative atom, oxygen. So this would be the stronger acid. This would be the weaker acid. Let's look at these two examples. Let's say that water donates a proton, right? So you lose a proton, and those two electrons become a lone pair on oxygen. If we donated a proton, we get hydroxide ion. So we have an oxygen with a negative charge. If we donate a proton, hydrogen sulfide, we get the thiolate ion. Okay, so now we're comparing two atoms that are in the same column, not in the same row. What we want to look at here is when we're comparing two atoms in the same column, size is going to be the most important. The size of the atom is going to be the most important. The bigger that the atom is, the more easily that it can spread out that negative charge and stabilize it, right? Sulfur is bigger than oxygen because remember, as we go down the periodic table, size increases. And since sulfur is bigger and oxygen is smaller, sulfur can more easily stabilize that negative charge. Oxygen has a harder time, it's smaller. So this is going to be more stable, which means that its corresponding acid is going to be a stronger acid. This one is less stable, meaning that water is a weaker acid. So you want to remember that electronegativity is the most important in a row. So if you're comparing two charged atoms in a row, you want to think about electronegativity. Size matters the most in the column, right? So if you're comparing two charged atoms in a column, you want to look at size. I'm not going to ever make you compare two atoms that are in different rows and columns, so don't worry about that. Okay, so now let's look at factor 2. We said the abbreviation, the factors that you want to look at, there's 5 factors. Atom is the first one, but notice in this case, if ethanol donates a proton or acetic acid donates a proton, that charged atom in each case will be the same. We'll have a negatively charged oxygen here, and we'll have a negatively charged oxygen here, right? So now we need to go on to the second factor, which is resonance. Notice here we don't have any pi bonds, so we can't have any resonance. Here we have a lone pair of electrons next to a pi bond, so that can become a pi bond. That can become a lone pair of electrons, and we get this resonance structure. Remember that the resonance hybrid means that this negative charge is shared between the two oxygens, so the resonance hybrid is actually a mixture of these two, and that stabilizes the negative charge. If we can share a negative charge between two or more atoms, that's a stabilizing effect. So that means the acetate ion is more stable, meaning that acetic acid is going to be the stronger acid. Ethanol will be the weaker acid, and in all cases, if the conjugate base has resonance, then the corresponding acid is stronger. All right. Like I said, notice this doesn't have resonance. This one does. This is more stable, so this is a stronger acid. Okay, let's look at factor 3. We already talked about atom and resonance. Next we're going to talk about induction, which is another thing that can stabilize conjugate bases. Notice the conjugate base of acetic acid, if we donate a proton, it's going to be the acetate ion. Conjugate base of trichloroacetic acid is going to be the trichloroacetate ion. Both of these have a negatively charged oxygen, right? So we're going to go to the second factor. Both of these are resonance stabilized, right? So that's not something that we need to consider. Now we need to look at induction. Induction just means that you have electronegative atoms that are close to the charged atom. What can happen is chlorine is electronegative, right? So we have a partial negative here, we have a partial negative here, and we have a partial negative here. Chlorine is pulling electrons towards itself through the cis-sigma bond network. And anytime we can spread out that negative charge, that's going to stabilize it. So this conjugate base is more stable, which means the corresponding acid is stronger. So any acid that's going to be stabilized by induction is going to be stronger than one that's not. Okay. Now what you want to keep in mind here is that the more electronegative atoms that you have, the stronger the acid gets, right? No electronegative atoms, weakest, followed by slightly stronger, stronger, strongest. 3 chlorines versus 2 chlorines versus 1 chlorine. Let's say, in this particular case, notice that for ethane, you can have a negative charge on carbon, no resonance, no induction. For ethylene, you're going to have a negative charge on carbon, no resonance, no induction. For acetylene, you can have a negative charge on carbon, no resonance, no induction. So now we need to look at the orbitals. Notice that this negative charge is going to be an sp3 hybrid orbital. This one sp2. This one is an sp orbital. And if you look at the shape of the orbitals, remember sp is a combination of half s, half p. This is a third s and 2/3 p. This is a quarter s, 3/4 p. So sp has more s orbital character. The s orbital is closer to the nucleus. Since the nucleus is positively charged, a negatively charged electron closer to the nucleus is going to be more stable. So this conjugate base, because it's in an orbital that's closer to the nucleus, is going to be more stable, and thus acetylene is the strongest of these 3 acids because we're deprotonating an sp hybrid carbon. This next most acidic is sp2, least acidic is going to be sp3. Okay, so let's do some practice here. Let's say you have this equilibrium. What you want to look at is you want to label the Bronsted acid, the Bronsted base, conjugate acid, conjugate base, use curved arrows to show electron movement, determine where the equilibrium will lie, and determine whether delta G is positive or negative. Okay, so if we look at both sides, HF is donating a proton, chlorine is accepting that proton, the proton donor is the acid, proton acceptor is the base, this is the conjugate base that came from the acid, this is the conjugate acid that came from the base. We're going to show arrows to depict electron movement, right? We're going to form a new chlorine-hydrogen bond. We have 4 lone pairs here, we only have 3 here. So one of these lone pairs is going to become a bond to hydrogen. We have 4 lone pairs here and only 3, so this bond is going to become a lone pair on fluorine. Okay, so we've done up to here. Now we need to determine whether the equilibrium will favor reactants or products. In order to do that, what you want to do is evaluate the strength of your 2 acids. This is HF, this is HCl, right? We said, and now you want to look at your conjugate bases, right? Cl minus, F minus, which one is more stable? Well, fluorine and chlorine are in the same column, so we need to look at size. Cl minus is more stable because it's bigger than F minus, and the equilibrium is always going to favor the side which is more stable. This is a weaker acid, this is a weaker base. The weak acid and the weak base are going to be favored, so reactants are favored here. If reactants are favored, delta G is positive, meaning the reaction is not spontaneous as drawn. The last thing I want to talk about is solvent effects. So notice we have the same atom that's going to be charged in each case. We're going to have, if we donate a proton, we'll have an O minus here. We'll also have an O minus here. So we look at atom, they're the same. We look at resonance, they both don't have resonance. We look at induction, there's no induction. We look at orbitals, they're both sp3 hybridized orbitals. So we need to look at solvent effects. What does that mean? Okay, I'll show you on the next slide. Okay, solvent are going to be surrounding these bases when they're generated in solution. The more sterically hindered, or the bigger that the base is, so a big base is going to be surrounded by less solvent molecules. Each solvent molecule can help accept some of that negative charge, so it's going to be less stable. Whereas smaller bases are going to be surrounded by more solvent molecules, so they're going to be more stable and thus stronger acids. So this is going to be a stronger acid than this, just by the virtue of the fact that it's less substituted at this carbon, or it's smaller. This is only going to be important if you look at atom, resonance, induction, and orbital, and they're all the same. One thing that you'll notice is that oftentimes the same reaction can be written different ways. Oftentimes we omit counterions, right? Here we have NH2 minus reacting with water to give ammonia and hydroxide. We could also write NaNH2 plus water gives ammonia plus NaOH. Remember, in each case there's a sodium cation which is also participating, right? But because these things completely dissociate, this is not going to be involved in the reaction. So in the top one we're just omitting spectator ions. Don't be confused about omission or inclusion of spectator ions. Remember, this is an ionic compound, so you're going to have a sodium cation and an NH2 minus anion, and similarly you'll have a sodium cation and a hydroxide anion. The last thing I want to talk about in this lecture are Lewis acids and Lewis bases. The whole time we've been talking about Bronsted acids and Bronsted bases. Lewis acid base definition is a broader definition. So a Lewis acid is going to be an electron pair donor. A Lewis acid is going to be an electron pair acceptor. So when water reacts with hydrochloric acid, remember we're donating a pair of electrons to hydrochloric acid, and it's accepting a pair of electrons here. Notice that this can be the case even if we don't have a proton donor and a proton acceptor. So water can react with boron trifluoride, donating a pair of electrons, accepting a pair of electrons. So this is our Lewis acid. This is our Lewis base, even though a proton is not transferred. Okay, so what do you need to know? What you need to know is how to identify acids, bases, conjugate bases. Understand how to use electronegativity, size, resonance, induction, hybridization, and even solvent to determine acid strength. Take those factors and be able to determine which side of an equilibrium is favored, be able to draw arrows to depict electron flow, be able to compare two or more acids and figure out which one is the stronger or the weaker acid, and then finally understand the definition of Lewis acids and Lewis bases.